Santosh, share the link in group. Harish or Santosh, can you start the recording?
Yeah, yeah, sure. Like, I think Harish needs to start doing that. Harish should record. Like, I don't have proper internet connectivity. Yeah, he started. Guys, if any one of your friends are yet to join, please ask them to join.
So can I start now? Is it-
I think you can wait for like 5 minutes. The participation is actually less. Like, let them join. I think they're slowly joining in.
Okay, fine. Yeah, I'll wait.
Guys, if there are any of your friends who did not join, please ask them to join.
Okay, guys, like I think I'll start. So welcome to the PCB designing session 2. So in this session, like we are going to design a PCB called CH340G, and we'll see its uses and about it now. Okay. So we need to know about the basics of serial communication for, to know about the PCB that we are going to design. Okay, so serial communication is the way of data transfer using a transmitter and receiver, and this is done over a wire, one bit at a time. All right, so this involves transmitter and receiver, and data is transferred through binary pulses. So you can see in this picture, first LSB is passed. LSB is the meaning, LSB means least significant bit, and MSB means most significant bit. All right, so uh,
Dheeraj, have you shared your screen?
Yeah, I forgot. Okay. Okay, now you can see, right? Sorry. Okay, we'll see about the CH340G that we are going to design in this session. All right. So for that to for understand what it is, like we need to know about the serial communication. So serial communication is the way of data transfer using 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 wire, and it uses two components called transmitter and receiver through which the data is transferred. So this data is transferred one bit at a time. Okay, so yeah, like this is some basic that we should know, like to know about what exactly our PCB does. All right. So initially from the transmitter, LSB is passed and then goes on to MSB. So LSB means the least significant bit and MSB means the most significant bit. So data is transferred in this kind of way to the receiver, and receiver receives it, and so the communication is done. Right. So this communication, to know about it. The process it is actually more complex, but in simplified version we'll see about it. So uh, serial communicating involves two serial devices, which is transmitter and receiver, as I said. So and both devices are actually connected using a wire. Okay. So and the data transmission is done one bit at a time, according yeah, one bit at a time. So for serial communication, the uh, two main hardware implementations are TTL and RS-232. So these are all the hardwares used for serial communication, and these two are the most popular. Okay, so let's see next. Is it fine? Okay. Okay. So basically, what we are going to do is a simplified version of a FTDI cable. All right. So FTDI cable is a cable which is used to convert USB to serial communication. All right. So um, in this case, the serial communication is done using TTL hardware. Okay. And so I think you can read the next two lines actually. Like US, this CH340 is actually makes our life simpler, and budget will also be covered actually. So normal FDDI cable will be over your budget. So this like more costlier than what we are going to do. So I think this will be really useful for the data transmission. Okay. So it converts USB to serial communication. This okay, yeah. So this 3CH340G is actually a chip actually that is what we are going to do, and this chip is used in CH3 USB CH3340 USB to serial and serial module and adapter. Okay, this is actually a serial tool in which this chip is used. Okay, yeah. So now we'll see the schematic about it, and we'll start doing the PCB. All right. This is just the basic that you should know, like what exactly this board does. All right. So yeah, if you have any doubts, you can ask in chat box. So if you guys don't have any doubts, we'll start with the schematic of the CH340G. All right. So you guys can create a new project in your ECEDA and get this kind of a screen. Okay. I'll wait for 2 minutes for you guys to open this. Okay. Have you guys opened ECEDA? Okay. Like the main goal of the today's class is like we are going to design another PCB the which is the USB to serial converter. So that is the main goal. So this PCB that we are going to do is more complex than what we did in the last session. So it would be good if we guys like learn more how to do how to design the PCB. Okay. I have said like what is the main goal of the today's class, right? So yeah, you can see my screen, I guess. So okay, so like now we are going to see that how we are going to get components from JLC PCB and non-common library because using JLC PCB like we can get the components along with the prices and see to that we can compare and get the cheapest one and most required one like what we really require. Okay, so I'll start with that. Okay, so I guess you guys can refer the schematic that is sent in the group now. Okay, so that is the basic schematic. Now we are going to do. So, okay, and the components and all like you must get it from JLC PCB. I'll show for two components like how should we take it. So, okay, so first I'll take the CH340G. Okay. Uh, No, like I wait, like I'll take some resistors now. like to show exactly what we should. Okay. Um, okay. So this is the JLC PCB, and here we are going to search the components. Okay. So if we put resistor, we will able to get many resistors actually. So yeah, if I just click something like this and see, uh, we will get these many resistors. So we must choose what we require. All right. So actually, like for searching the components, the home symbol is required. Okay. So I'll just copy from this, and I require first I'll search for 1 kilo ohm resistor. Okay. I'll search here. Ohm symbol, for ohm symbol only, like I copied it and I'll use this. Okay. 1 kilo. And for this, I am getting these many results, 77,000 results I am getting also. Uh, and we are going to use the basic part, okay? That will be mostly the cheaper ones, okay? So by seeing this, we'll get 5 resistors in total in JLC PCB. So in this, like we are going to choose by seeing the price and the standard size actually. So in usually we will use 0603 package. All right. So this one is 0402. And this, if we see again, the second part, this resistor, okay, this resistor is 0603 package. This actually denotes the size of the resistor. All right. This 0603 means it is 6 millimeter. Okay, guys, am I audible now? So, yeah, I'll start again. So, okay, guys, like I'm audible, right? Harish, Santosh.
Yes, Dheeraj, it is audible. You can continue the session.
Okay, fine. Yeah. Okay, so after searching 1 kilo ohm and clicking on the basic parts, uh, we were getting five results. All right. In these five results, we must get the cheaper one as well as the size which is mentioned as 0603, because this is the most standard size that we use. This 0603 notes the resistor is 6 millimeter in length and 3 millimeter in the breadth. Okay, so this is the standard size that we use, and we can see that the this resistor is actually the most I mean, it is actually cheaper than others. But seeing this four, which is also the same price, this size is 0402, which is smaller than what we require. So I'm actually going to
Dheeraj,
use this.
hello.
Yeah. Okay.
Dheeraj, can you
Hello. Yeah.
repeat the
Am I
process?
out?
Instance, yeah. You are audible. Can you repeat that process of
Okay.
searching the parts from JLCB home website to going to that JLCB assembly parts library,
Okay. Okay.
as well as taking resistor also?
Okay. Fine. I'll do it again. So. See guys, like from here, this is the schematic where we'll do. So in the left side, you can see an option JLC PCB. You click on them, and you guys can get this page where you go to resources and go to assembly parts library. Okay, and here you guys can search resistor. Like this we can get the equipments. All right, so these actually we get these many results for resistor, and we actually require 1 kilo ohm resistor. Okay, so for that to be searched effectively, like I actually need this ohm symbol. Okay, I'll just copy from this, and I'll search it here. Okay, uh, 1 kilo ohm actually there in schematic, right? So 1 kilo ohm, I'll search like this, and now we get these many results, 77172 results, in which basic part we need basic parts, because basic parts are usually cheaper than the extended part that is here. Okay, so we'll click basic parts, and yeah, we need the resistor size to be 0603, so which is this one, and we also need it to be cost effective. So see the cost here, and the standard size that we use is 0603, which is also cheap only. So we'll see this. This is the resistor we are going to use for 1 kilo ohm. Okay, so I'll copy this JLC PCB part number. Okay, if we search this part number in the library, we'll get the component which we require. Okay, I'm again going to the ECDF, and here I'll go to library and search uh, the code. Okay, so yeah, I am getting a resistor here. So this is the 1 kilo ohm resistor that we are going to use. Yeah. So drag it here. You can see this. Okay. So in the schematic, there is 1 kilo ohm, and this another thing we need is 330 ohms. So we'll do similar thing in the JLCPC. So you guys can see from the schematic that these two resistors have been used. Okay. 330 ohms, and we need basic part. So we get three of them. And from that, if we see, this one is 0402, we need 0603. So I'm going to use this one. Even though price is just like price is somewhat higher than the basic part, which is 0402, we'll use this one because this is the standard. Okay. So copy this part number and search it in the ECEDA library. So this is the 330 ohm resistor we are going to use. Okay. So yeah, now we'll get the schematics, all right? So other equipments. So we need again CH340 GIC. We'll search this in library. Okay. Okay, so we are getting this. Okay, so click on this and press place. Okay. So this is the main IC which is used for the PCB. Okay. So we'll just get all the equipments first and start with the wiring schematics. Okay. And this is actually an AND gate. Okay. So AND gate's ID is mentioned over here. So we'll search for it in the library. Okay.
Dheeraj, go a bit slow, bro.
Okay. Yeah. Okay. So like I'll give 1 minute to get these equipments. Okay. Just try. Okay. I'll now search for that AND gate. So its code is 74. You can refer the schematic for the code. Okay.
Dheeraj, once can you repeat a JLPCB part once more? Like people are asking for it.
Like how to search in it.
Yeah. You started from there. Like you just give it a brief.
Okay. I'll say about it again. So to for going into JLC PCB part, in the schematic itself there is an option for it. for going to JLC PCB. You can click on it, and here you will get the page like this. Go to resources and assembly parts library. Okay. Yeah. Here we can search for the components that we require. Okay. For getting the ohm symbol, like I was just doing by searching resistor, and from many of the components, if you see the ohm symbol, you can just copy it, like, because searching using this value, it will be a good thing. So we'll get what we require easily. So I'm doing it again. So the component that we required was 1 kilo ohm and 330 ohm. So you can search like this and scroll it down. So we need a basic part. So we'll click on basic parts, and we see 5 different resistors. Okay, we require the cheaper, like cheaper one is preferred, and the size that we use usually is 0603. So here if you see, like two of them are almost same size, and this one is 0402 package number. So 0402 denotes the length of the resistor is 4 millimeter and breadth of the resistor is 2 millimeter. So we usually use the standard one, which is 0603. Okay. So I will copy this JLC PCB part number and search it in the ECEDA library for getting the required resistor. Okay. Yeah, like this only we should use the JLC PCB part. Okay. Now we'll search the and get. Okay. The code for the ID for the and get is in the schematic. Yeah. So we are getting the component. This is the AND gate that we are going to use. Okay. And next that we can take is okay, now I'll take this 6-pin header. This is for use for serial connection. Okay. So I'll search this. Actually, this we can use from common library. In common library, I think you can see this one. Under connectors, you can see you can see this, all right. So in this, press the drop down and search for HDR M1 cross 6. Okay, we require 1 cross 6, which is mentioned in the schematic. So I'll get this. I'll press this, and you can see these 6-pin connector. So we will use this one as the 6-pin cutter. Like this is used for actually serial connection. Okay. And for 3.3 voltage regulation, there is a part number that is mentioned below it. We will try to search this. Okay, from library itself. does it mention? Hyphen 2. Okay, actually, like I wanted a better equipment, so yeah, 1 minute. Okay, so search like this for the equipment for this part of the schematic 0.3 voltage regulation. Okay, so this component is mostly used. So we'll take this using we'll take this like pressing place and okay, yeah, okay. So still one part we need to get, which is the USB. Okay. Okay. So for USB, we'll search this. Okay. Just try to copy this. Okay. The code for us. So we will use this component. You can see this name of this and from my schematic and search this in the library. Okay. So I think we got all the parts. And, oh wait, I think one more thing we should get. Uh, you can see this 12 megahertz Y2, right? This we need to get this one also, and capacitors also we must get it from the for capacitors we need to get it from JLC PCB. Okay, and this we'll get from the code. Okay, I'll type for it. Okay. Type C9002 for the crystal oscillator. That is the name for this. So we'll take this. Okay. Yeah. So I think all the required components have been taken, and we'll start. We'll start the schematic wiring part of the schematic. Okay. This wiring part, I think you guys can do like using the schematic that I have shown. Okay. Anyways, I'm going to do the schematic for you guys. So okay. Yeah. Okay. So the remaining parts that we must take is the capacitor and LED also is there. So I'll show how to take it. So again, like go to JLC PCB. So here I can type LED. So these many cells showing. Okay. So in this we need basic part and okay. So I think this one is the cheapest. Right? Yeah, this one is the cheapest. So we'll take this LED and this part name is also 0603 like package name. So this is the standard that we use. Okay. Copy this JLC PCB part number and search it in the library. So basic part is what we require. So this is the LED we are going to use. Okay. And so simply try to search for the capacitors. Okay. There are 4 different values for the capacitors that is mentioned. So I'll take it one by one. You guys can do it on your own also. So there is 10 nanofarad, such 10 nanofarad in the LGPCB. And we need basic parts. And cheaper one would be better. But the cheaper one is 0402. But so we'll take this one. The most usually taken. So I'll copy this and search. I think you guys are getting familiar with using this JLC PCB part. So okay, and there are capacitor with 10 picofarad. 10 picofarad. We take basic parts. So we need 0602. Copy. Search. place. And another thing is 10 nano, I mean 0.1 microfarad is present. It's search for it. So for 0.1 microfarad, I'll search it as 100 nanofarad, which is the same. Okay. Similar thing, we're doing basic parts and getting the 0603. I'll copy from here. And another thing is 1 microfarad. For micro, they have represented it as U. 1 UF means 1 microfarad. Okay. And we require 0603. Zeros place. Okay. Now all the equipments are like all the components are present. So we'll start with the wiring of the circuit. And as I said in the previous class, like try to follow what I used as the tag. All right. The don't change the name. Okay. So now I'm just seeing the schematic and doing the connections, okay, which you guys can also start doing. I think there's no problem with getting the components. Okay, so okay, for resistor and capacitor, I think you guys can just take it from JLC PCB like the way I said. Okay, so I'll start with the wiring. Okay, you guys also start with it. So as I mentioned in the schematic, like don't use VCC. Okay, instead of that, use this. You can get this 5 volt and change the value for this. Change the plus 5 volt as 3.3, which is what we require. We'll use 3.3. I'm doing the same thing as in schematic. Okay, you can refer it. So changing the tag names, usually it is it's your wish only. Uh, it would be better if you guys like use my tag names, okay? Because it would be easier for you guys also to follow me. Okay? And this cross is meaning if we are not using any pins in the IC, you can use this cross, okay? In this case, R232 is not used, okay? So I am using this cross symbol so that no connections is made with this 15th pin, okay? That is the meaning of this cross. And similarly, like which all terminals which are not used, I am going to use this. This I am doing by seeing the schematic only, like here and all, no wires were actually present. Okay? And in this also, the fourth pin is not connected to anything. So, and I'll change this. I hope you guys are following. Okay? So here like two 1 microfarad capacitor is used. So to copy the same capacitor, you can click on this, press copy, and press paste for getting another capacitor. Okay. Okay, this component is called crystal oscillator, and here you can see four pins. Okay, pin 4 and pin 2 should be connected to ground. Uh, Actually, we can see that this is a bit different from what we are having in the schematic. But yeah, like so, the extra terminal is also connected to ground. Okay, so try to follow the connections for crystal oscillator from here. Okay, so I think I have done with the connections. Like I will give you 5 minutes, like for referring it and completing it. Okay.
Dheeraj, can you zoom the diagram? Hello?
Okay, but
Dheeraj? Yeah.
Yes, guys, if you are done with it, we can start routing part.
okay, you guys have completed the schematic.
Yeah, fine. We will start within 2 minutes. Yes, guys, I think I can start with routing part right now because we are running out of time. So now this is the schematic done. So we can convert this into PCB. Just go into design option and click on the option convert schematic to PCB. Now check the nets. See, actually yellow color ones are it causes no problem for us while designing PCB. So check this one, this shield. This one is not connected anywhere in the remaining part of the circuit. You can check the schematic ones. This one is not connected anywhere in the remaining part of the circuit. So it is throwing errors. It is throwing us a error, but this can be neglected. So we can proceed with PCB design. So let it be default. Then we can decrease the size of the board. So remember these things in mind. While we are designing PCB, the board length, both size should be kept as small as possible. That is actually preferred one. Both sides should be kept as small as possible. And remember the rules of routing taught to you yesterday. So we can start with that. We can place the components inside one by one. See, this is the USB port. This is where you will be connecting the USB cable. So it should be kept at the boundary part. So click space for rotating it. Keep this at a boundary part so that cable can be inserted easily. And this is where we will be connecting the other board like ESP32 and other stuff for transferring the USB data from USB to either in serial form or UART form. So you can click space for rotating it actually. And this is the main IC CH340G. Try to keep this at the center. See, you can see there are so many rat lines actually. So this is the one which should be kept at center so that we can connect easily. We can connect other traces with other parts easily. So try moving it and rotating until where you feel the trace length is getting minimum. And next, keep the power source. Here the power source you can see from the schematic. It is the U3 one. This is the power source present here. So this is actually voltage regulator. It will convert the incoming voltage, like for example, 5 volt to 3.3 volt, which we actually supply to complete board. So this is that one. You can see in the schematic that there are two capacitors near to this U3. So these are called as uh, decoupling capacitors. So they need to be kept near this power supply. So note that numbers, it is C4 and C5. They need to be kept near to this. See, you can see when I'm bringing it here, you can see the rat lines. See, so 5 volt is connected. So try tilting it. See, now the connection can be made easily. See, 5 volt can be connected easily. C4 and C5. So bring the C5 also near and place it near this U3. 3.3 volt. So here 3.3 volt is there. So you can keep C5 at this side and try tilting it. Now you can see in the schematic there is also one more capacitor, which is decoupling capacitor, which is a decoupling capacitor. Since one side is connected to 3.3 volt and other side is grounded, so you can keep this one also near the power source, power supply. And now you can take the LEDs. Before taking LEDs, take this crystal oscillator. You can see the rat lines. See, where's the, you can see that rat lines, and this pin U1 underscore 8 is getting connected with this pin of the IC, U1 underscore 8 of the IC pin. And you can see U1 underscore 7 is getting connected with U1 underscore 7. So don't worry about ground connections as well as ground connections as well as 3.3 volt connections. So they can be made with copper layer. So just see this U1 underscore, try to concentrate on rest of the other things. So try tilting this. See the place where the rat lines is getting minimized or connection is becoming easy. So I think this one would be fine. I can connect it directly and this one also directly. And next take this ungate pin. So can able to see that wherever where it is going. See the rat lines. So these two are going to TX minus pin of the IC. So try to keep them in a way such that the routing becomes easier. I think this would be fine. So next, place the LEDs. See this, these both are getting connected. This U2 underscore 4 and U2 underscore 4. So if I tilt it, the connection becomes much more easier. Guys, could you able to follow? Yeah, fine. I check this one. So take the other LED. You can see that this one is getting connected to TX plus. So TX plus pin of the TX plus pin is here. So try to keep near this part. So I think we can interchange this. So I can what I'm doing is that I'm interchanging this LED to this place, and I'm keeping this LED here so that this connection becomes easier. So next take the other capacitors and resistors. I think you can take this R1. This R1 is getting connected to this terminal of LED one. So try to place it. And other connection is 3.3 volts. So you need not worry about it. We can fill it with copper area. See now it is fine, I guess. And take R2. So R2, I think it should be kept near this LED2. So see this R2 underscore R1, R2 underscore R1. They both need to be connected. So if you place it like this, it would be easy. And try bringing the rest of the capacitors. So check this connection where it is going. One is going to U1 underscore 7 pin and another one is ground. So you need to worry only about this U1 underscore 7 pin. Let us keep it here. So then the connection becomes easier. So let us move this a bit. So that this U1 underscore 7 pin and this U1 underscore 7 can be connected easily. Try to make the board as compact as possible. Both sides should be small. So check this connection. One is going to U1 underscore 4 and another one is getting grounded. So U1 underscore 4 is here. Try to place it like this. So U1 underscore 4. Both are getting connected. So one more capacitor left out. It is going to U1 underscore 8. So find where is U1 underscore 8 and see. Now see U1 underscore 8 is present here. So we can keep it in such a way that it is easy to getting to make it connected. Now try tilting this one so that this U1 underscore 8 might the connection might become much more easier. See now U1 underscore 8 can be connected easily and U1 underscore 7 can be connected by this way and this one is also getting connected. So if you want to see where all the connections are going, if you want try just placing your mouse on one of the pad of the component so you can see where it all is getting connected. You can see that white lines, right? So they all are getting connected. So in this way you can place the component. Is it clear? If you have any doubts, you can ask on chat. Fine. Yeah, now try to align the components. So you want to make your board also look somewhat neat, right? So try to align the components. So you can find some aligning options here. You can find aligning options here. And so to align, click on a component and press Control option. Click on the other component. Next, the other component, the other components, and all the components you want to align. So I'm pressing left click plus Control to select all these things together. Now wisely use this option. See, I'm going to use this option for making it to get aligned along top line. So everything gets aligned along top line. If you use this one, they get aligned along bottom line. This one for getting aligned, all the centers will be getting aligned. Similarly, you can do for other components as well. Try to make this somewhat so that this center is also matched. Similarly, you can align all the components which are down. Left click, control, and choose this option wisely. See now, I think we can now reduce these both size. Just see the connections once whether all the components are placed properly. Then we can proceed for routing. I think we can proceed for routing. So we can remove the prefix actually, so that it becomes a bit clear. Yeah. Now see the board. So they are actually, we need not worry about these top silk layer as well as this prefixes while we are routing. Yeah, we can start actually. So let me start from this one, R1 underscore R1. So that's all. So remember the rules while we are routing. So you should not have perpendicular connections. And first one thing, preferred angle is 45 degrees, and there should be some minimum clearance between the two traces. And when you are keeping via, there should be some minimum clearance between the trace as well as via. These things you can find from design. You can see from design rule. So this is a one which is design rule. So you can see the track with clearance via diameter, via drill diameter. So track width is the trace width basically. Clearance is the minimum distance needed between them, as well as via diameter is the whole diameter of the via. Via is nothing but which you use for connecting the top layer as well as bottom layer. Via drill diameter is the whole size. Whole you can find, right? Yeah, I will show that actually. So this unit is in mil. You can see here. So your mil is actually a unit which is generally used by PCB designers. So we can convert that unit to also. So you can find in right canvas properties. So you can change their units from mil to is millimeter, and mil is the unit used generally by PCB designers for designing PCB. So you can see this is via. So this one is drill diameter, and this one is hole via diameter. Yeah, and you need to follow some design rules. So one design rule is that perpendicular connection should not be there, and another one is that it is preferred that top layer wire and bottom layer wire should not be parallel, because there will be some like interference between them. So it is advisable to avoid the traces being parallel in top layer and bottom layer. Yeah, we can start. So next I will connect, don't connect 3.3 volt and ground. So you connect them with copper area. Okay, let us connect then TX plus and TX minus. So here there is a communication rule here. So you need to apply that. The trace length should be approximately same. See here you can find TX plus and TX minus. Here also you can find TX minus and TX plus. So the trace length between them should be approximately same. This is actually done to avoid the delay in the signal. So you should keep that in mind. For implementing that, you can find a option in route called differential pair routing. So this is actually known as differential pair routing. It is used so that the trace length can be approximately same. If you click this, see, you can get a wire. So which you need to connect to this end. So now you can't directly go in top layer. See, because you will be hitting this, so which is actually not allowed. So you need to change into bottom layer. So how can I actually change into bottom layer is that just give a click here and then choose bottom layer, so you can get transferred into bottom layer and then connect it. So first try to completely connect it, then only you can actually end the connection. So it will be some random shape, let it be, we can delete and change it. So now delete this part as well as this part. So now see the connection. I want the length to be approximately same. So what I'm doing is that this can be connected in bottom layer itself. One can be connected in bottom layer. So another one, it is better to change into top layer. I think now you need to maintain the same length. Now measure the length. You can measure the length by in this following way. You can click on this wire. So you will be getting the length in mm. See here, the length is 6.675. So just check 6.6 plus. You can check the other part of the length. So you can find the length here. So this is the selected part and you can find the length here. And that length is 2.6, approximately 2.7. And another part length also we need to add. So this is that part. And that part length is 2.3. So the total length is approximately 11.6. Now check the length for this. So this one is around 9 plus 2.3, approximately 11.3. So try to increase the length of this wire or else decrease the length of the above wire. Now I think it would be fine. Yeah, approximately both the ends are same. So it is nearing to lawn. Yeah, so this is known as differential pair routing. Yeah, then connect the other parts also. So here there is a TX plus connected with this TX plus, and here you can find TX minus. So you are facing a problem in routing instance, then try to shift this component. You can shift this component to left a bit. So if something happens like this, just press on the option. So this is the connection for TX minus and TX plus. You can see that all the TX minus got connected and TX plus got connected. So we can proceed for next one. Similarly, here also you need to use differential pair routing, P minus and P plus. That is actually based on some communication rules. So you need not worry for that. In this case, you need to follow for this one also. Just choose from route this option differential pair routing and then click on the P minus. Wait, I think it's not, I did not get selected. Yeah, now you can find that. Try to first connect it. So you choose that option again. So it will random shape. Then you need to change that. I will now change into bottom layer for actually easy connection purpose. Not here, instance somewhere here. So again, I need to change into top layer. So now you want to figure the problem. So delete this part as well as this part. Now see, this P plus need to go there and P minus need to come here. So take a wire. And yeah, now Yeah, I think this could be fine. Check the length once, it should be approximately same. So this is like 2.7. So check the length. So this is 2.7 plus 5.3. 0.2, which is approximately 10.2. Now check this length. 3.4 approximately plus 0.9 plus 2.2, which is 10.5. So we need to try to reduce the length of this a bit. So this yellow color cross mark comes if you give follow any follow this yellow color cross marks comes if you neglect some of the design rules. So you need to avoid this error. So that comes when clearance is less and such kind of things. So this seems to look like 90 degrees. So try to make this as 45 one because this should not be kept. Yeah, now it's fine. Yeah, now I guess the length could be approximately matching. Yeah, fine. Now we can go to other part of the routing. Next thing. So you can see that all those terminals P plus and P minus got connected. Now you can go for other things like so you want to see whatever thing is not connected, you can go to design manager and check the nets. So you still need to connect we need to still connect CTS DTR, so we can go one by one. Let us go to this U24. You can see that U24 is here, as well as U24. That's all. U24 got connected. Now we can go for R2 underscore 1, and that's it. I think in bottom part, that's top part, that's all. So check for this one. So this is ground. You need not worry. So you can connect U1 underscore 4. You can now understand why I actually took from bottom part. So this U1 8 connection will become easier. We can connect it directly if we take these two wires in bottom part and then take here again in top part, as well as connect this U1 underscore 8 and 1 underscore 8. So you can still see that U1 underscore 7 need to be connected. So there is actually a small problem connecting. Yeah. So what I am doing is that I am taking a bottom layer from this part, this point. See, this U1 underscore 7 and this U1 underscore 7 need to be connected. So I am taking a wire from bottom part from this area and then So player, yeah, I think this need to be made to 45-degree. Yeah, now it is fine, I guess. Yeah, now it is fine. Yeah, you can now see that u1_7 and u1_8 got connected. So what else we are left with? So you can refresh this to see what else we are left with. So this shield need to be connected. So I'm connecting this. So I'm choosing a bottom port for connection on this. You can either use any top or bottom, but I guess here bottom is fine. Still we have CTS ground you can leave. So 3.3 volt also you can leave. So we can connect 5 volts now. So I'm shifting this to a left a bit. These two 5 volts need to be connected. Yeah. So still one more 5 volt is also there. You can see it here, right? So this one need to be connected here. So what can we do is that we can go in bottom layer and add a wire. Just yeah, now 5 volt got connected. So what else is left out? Yeah, you can see here some part is still there. Okay, CTS you can directly connect, and DTR is there. So you can even connect this directly. Oh, see. Yeah. No, only 3.3 volt and ground is left. You can just refresh it. So you can see only 3.3 volt and ground is left out. So we can now use the help of copper area for connecting all the VCCs 3.3 volt and ground. So choose this option, change it to 3.3 volt. Yeah. Press OK. Cover the entire board with area. Yeah. Just give a right click when you want to end. So you can now see that it is completely filled. Now you can check whether all the, yeah, luckily we got like all the 3.3 volts got connected using the copper area. So only ground connection is now left. So what we can do now is that for ground layer connection, you can choose a copper area to be filled at bottom layer. Yeah. Make it as ground GND. Okay. So yeah, now you can see that we applied, but still all the grounds would have not got connected. See, still you have grounds which have not got connected. So we can connect them using traces and via. Let me show them. Until now, could you guys able to follow? Should I need to wait? You can tell in chat if I need to wait for some 2 or 3 minutes. Okay, sure. Yeah. If you have any doubts, also you can put it in chat. Yeah, guys, is it done? Okay, I think I could start. Yeah. See, now ground connections left out. So what I'm doing is that you can see that bottom area is completely ground. Bottom plate is completely ground. So what we can do is that, so first connect these two parts using red color trace. See, these can be connected directly. And then now take a trace. Okay, let me hide the copper area for simplification purpose. So what can you do is that you can find layers and objects. Go to the option object and choose. You can here you can see that components, prefix, name, trackpad, via, etc. So choose this option for hiding the copper area. So now you can now what I'm doing is that I'm connecting these two grounds with traces, and then yeah, just put a via here so that it is like bottom area is ground, so that you can directly get a ground connection. Choose this option and just click ground. Yeah, it's fine, I guess. Yeah. So after choosing an option, you need to give rebuild copper. When you give a right click, you can see option copper area and give rebuild all, so that the copper area again will rebuild according to the changes we make. Like that, connect all the grounds, like connect the possible grounds with the traces, and then give a via so that it is getting grounded. Yeah. See here also a ground is there, but connecting this. I'm trying to connect the all the grounds and see. I need to give a tray a via here to make it to get it connected to the bottom layer. So I'm just giving a click and then choosing the via from PCB tools option and put a via here. So now you can zoom in. Ah. Similarly, you can see here also we have connected it. So here also we need to put a wire, choose a wire, and I can put it here also. Yeah, you can understand, right? You guys can understand, right? See, all these grounds are connected using red color wire. So I need to connect this with the ground which is present in the bottom layer. So I am giving a wire for it. So if I give a via for it, and so from bottom layer, I'm getting a ground here, and from this ground to other ground, it is connected using traces. Similarly, I need to do like this for all. See now this ground connection also needs a via. This one is isolated. You can see, right? This three grounds. So what I'm doing is that I'm taking a wire, giving a click, and choosing via from PCB tools option. and inserting it. So now you can see that the rat line disappeared from here to here. You can see that two more rat lines are there. So this ground is completely isolated from all others. So it is better to keep one more wire, or else you need to go using trace from this part to this part, which is not actually advisable. Instead, you can give a wire. Similarly here also. Now you can give the option right click, copper area, rebuild all. So now you can see all the copper areas got rebuilded. So now you can click on the nets. So all the grounds got connected, and now you can see, is there any DRC errors? So design rule is checking. So we got no errors. So our connection is completely fine, and this is the thing. So now you guys can explore this. Now I'm saving it, and let me show the 3D view of this. Yeah, it got saved. For saving, you can use the option Control plus S. This is the 3D view of the board. So here is where the USB cable will be getting connected, and this is the part where you need to connect this header will be getting connected to the ESP32 board or other microcontrollers. Like even Nano Arduino doesn't have this, so that is why it got its name Nano. So you need to implement this externally. This is what we have done. So this is the voltage regulator, which when we apply the input voltage as 5 volt, it gives the output as 3.3 volt, which is supplied to all the rest of the circuit. So that is actually the top layer. And these are the wires and other these two are capacitors and resistors you can find. These are called SMDs. This is because they are surface mounted devices. These are. And this is crystal oscillator. Yeah, and this is yeah, now I guess this is all about routing, and you can see here that this is actually called as power line. So power lines are generally need to be kept thicker than thicker because that is actually advisable, because we will be sending a power supply and we need to know it is a power supply line, so it need to be kept thicker. You can change the thickness of it using this. So here you can find the width, right? You can increase the width. The problem is that it will cause some error in this case, I guess. Yeah, getting some errors.
Harish, can you explain the last part of grounding? Like they were asked.
Yeah, sure. Yeah, sure. Yeah, sure. Just a minute, guys. What I was saying is that let me show you an example. See, you can see that grounds are there. What I did is that I filled the complete back part of the board, bottom layer of the board. with the ground. Wait, let me show that. So I disabled it, and now you can change it to bottom layer. Yeah, you can see that bottom layer is completely filled with ground. Now you come to top layer. You can see your ground connections. So what I did is that I connected the ground from here to the back part of the board using wire. What basically wire does is that it connects the bottommost layer and topmost layer. That is what the work done by wire. So this the ground from the bottom layer is getting uh, connected to this part using a wire and using traces. That is the thing which I have done actually. So try to connect the grounds which are near to each other using trace, and then connect that to bottom layer using a wire. Is this understandable? Yeah, fine. Yeah, if you guys are done with it, let me show you another interesting option called auto route. Or should I need to wait for some time? Yeah, you can see the okay. This is the routing part, and you can see there are like PCB tools. You can explore each tool. This one is the wiring tool, and this one is basically a pad. You can see that. So this one basically connects. We can use it for connection purpose. Instance, this is actually similar to this one. This one is similar to this one. And you can also find this is via, and if you want to give a text on the board, like some people actually see, if you need to, you can even give a text in the board, or even insert an image which you need. So this is known as top silk layer. This generally contributes the writing part, or the boundary part, which actually is not that much important. So you can give a text or any image in top layer, top silk layer. And this one is another wiring tool. So see, since I selected a silk layer, it is giving me in yellow color. If I choose some top layer, it will show in red color. So these are the curves. If you need any curves, you can use this. It's actually better than 45 degrees. This curve is actually preferred to reduce the signal loss. So such kind of rules are also there. It is actually used in another board actually. This kind of curve structures, and this one is for this kind of circular kind of structure, and this one is basically hand. Was if you can use it for moving the sheet actually. So this one is actually used for drilling the board. So you can even place it at four corners so that the board can be hinged, which means in 3D view you can able to see that you can able to see a hole in the board. So basically, this can be kept so that the board can be hinged somewhere. Like that, this is you can set the Canva to origin. So basically, that is the function of this. And this is if you want to construct anything in some angle, you can use this. Mm. Yeah. As well as this is the copper area tool, and this is something. Yeah, we can use for connecting pad to pad, and this is the pad actually. So this is some if you want a solid layer, like a solid layer need to be filled with copper area, you can use this option. See, you can get any random shape which you need. So you can explore these all these options, and this can be used for ready measuring the dimensions of the board. You need to keep the dimensions of the board as small as possible, as compact as possible. This one is approximately 2.7 centimeter and 2.1 centimeter. So this is approximately 2.7 cross 2.1. So even you have a space at top, you can reduce the board length even. Yeah, you can insert an image using this option. For this option is used for inserting an image, and this is for some rectangle kind of shape which you need to fill copper area. And this one is like a document setting which you saw in schematics. So this is these are all about PCB tools, and this is about this one is layers and objects. So here you can find all those layers. So actually, you need not only do like two layer PCB. There can be even multi-layer PCBs. So this is top layer, bottom layer, top silk layer, and bottom silk layer, all those stuffs. And if you want to hide, you can use this option. So you can even, yeah, if you want, you can explore these options. And this one is copper layer. So basically, we have top layer and bottom layer in this case. If you need, you can even construct it with multi-layer copper layers are also there. Boards with multi-layer copper is also there. And this is non-copper layer, top silk layer, which is generally used for writing as well as inserting an image, etc. So this is the objects which I have shown. So here you can hide any components or components as well as via hole, as well as copper region, from here. Yeah, these are about layers and objects as well as PCB tools. There is an option called auto route, which I will show you guys. So similarly, you can place the components in the way I placed. So this one is the power supply, U3 voltage regulator. You can see C5, C4, and C3 need to be kept near power supply. So let me take this to this side. So actually component placing is also an important task. You should place it properly the way I explained, so the routing becomes easier. So similarly, you should place all the components in the way which I showed in manual routing. Take this U2. Yeah. And this one is U18. This one need to be placed near U18, and this resistor, see this resistor. So R1 underscore R1 need to be kept near this LED. So see this resistor R2 underscore R1. So this is need to be placed it here. So similarly, you can even align the components in the way which I showed in the previous one, manual routing one. So U1 underscore 4, it can be kept at this place. U1 underscore 7, this can be kept at this place. As I'm running out of time, I'm not showing that component alignment again. So yes, you can follow the same procedure which I showed you in the previous one. Now you can reduce the board length as well as size. Yeah, this way you can reduce the board way and board size. Yeah, now there is a option called route auto route. In route, you can find an option called auto route. After if you click this, you can need to specify, or you can check once the design rule. If you want to, this is the design rule. It will follow this design rule, and with that, it will route all those traces. See, it completed 100%. So total wires 4. But actually don't use this, guys. So you can see that there will be some problems. See here 90 degrees is there, which is actually should not be there. And you can also see that it is kind of a branch. So it is like, yeah, branch is getting get like coming out from a trace. So this is also should not be done while routing. So auto route gives you some problems as well. See, 90-degree connection is there. It should not be there. It is preferred not to use auto route. As well as it is also advisable not to take top layer wire all over inside the CH340G sensor, because it causes some interference between the IC as well as this trace. So it is advisable not to do this. And here you can see that bottom layer wire and top layer wire are parallel. which should also not be done according to the routing rules. So that is why manual routing is better. You can see that how our manual routing is, and it is far way better than auto routing. So don't use this, guys, auto routing. So if you guys have any doubt, you can ask. Dheeraj will give you the access to mic. If you raise the hand, you can ask any, ask any doubt if you have. Yeah, guys, is there any doubt, or do you guys want us to repeat any part? If nothing is there, we can wind up. Yeah, you can ask us. You can raise the hand. We can give you the access to mic. So you can ask any doubts. Yeah, fine, guys. I think you guys. I hope you guys enjoyed this session. Thank you.